So we've got a fantastic programme of public lectures, outreach activities and conferences throughout the year. So do stay tuned to our social media channels and newsletters for more announcements. And today we have the fantastic Professor Matt Balme, who is Professor in Planetary Science at the Open University. He's going to be taking us on a journey through the rocks and landscapes of Mars and the history of the missions and rovers that we've sent there, including the very popular and famous Perseverance that landed this February. For those that are interested, and you can see on the screen now, we're running a treasure hunt in this lecture. There's a number of Geological Society badges being shown on the screen right now, hidden in Matt's slides throughout the talk. Your challenge is to collect them all and check them on the form that we're putting, that is on the link in the Zoom and YouTube chat, depending on where you're joining from. As always, if you have any questions for Matt, we're going to be doing a Q&A session at the end of the talk. Please put your questions in the Zoom Q&A box or in the chat on the YouTube channel, depending on where you're watching from, and I will collate them and put them to Matt at the end of his talk. For those of you on Zoom, we're also going to be running a poll that you can participate in during the talk. That won't be accessible for those on YouTube. Sorry about that. So without further ado, I will hand over to Matt, who's going to take us on a fascinating journey across the red planet. Thank you.
Okay, thank you very much. Yeah, I've hidden these badges around the place. I hope they're not too difficult. I don't think I've hidden any of them really unfairly. So thanks for the introduction, Flo. I've been studying Mars for, I'd say, about 20 years. Started looking at present-day processes involving wind and ice on Mars. But for the last 7 or 8 years, I've been looking at ancient landscapes, and this is mainly really to support the work I've been doing looking at landing site selection for the European Space Agency ExoMars rover missions. That's going to launch in 2023. I picked this image to start for a couple of reasons. First off, it's really pretty. So this is a lovely picture of Mars taken by European Space Agency Mars Express mission. But also it shows some key things about Mars and sort of sets a tone for this talk. So first of all, you can see a haze. Can't really see the surface that well. That's because Mars has an atmosphere. Now you can also see in the bottom here, oh, I think I just turned on my laser pointer. So I hope you can all see that. Yep, so that is clouds on Mars. And the clouds are forming behind this, which is a large volcano. And the reason it's forming behind that is because there are winds. So there's an active atmosphere on Mars. And the fact that it's forming behind this volcano, that shows us that Mars has giant volcanoes. These smaller things around here are impact craters. And what this means is that not only does it have an atmosphere, it also has a solid surface that's experienced various geological processes over time. So I'm going to start off by talking a little about Mars exploration. This first image here is taken with a camera, but this is my representation of what ancient humans might have recognized. They would have looked up into the night sky and they would have seen the moon. They probably would have seen a bright star called Jupiter, but they might not have noticed Mars. It's quite small. But having said that, as far back as the Egyptians, so thousands of years ago, they knew that Mars was a wandering star. So it wasn't like all the other stars. So I think even thousands of years ago, there was some hint of scientific study of Mars. Really, the scientific study of Mars, well, kicked off basically with the invention of the telescope in the 17th century. So humans were actually able to see surface features on Mars. So the first maps were made in the 18th and 19th century, and this is a map by Schiaparelli, and it shows all sorts of exciting details on the surface, or at least details that Schiaparelli inferred to be on the surface. It does look a little over-detailed to me, perhaps. I think the interesting thing about this map is a lot of the names are names that are still being used today. So Elysium, Tharsis, Noarchus. You'll see some of these names being used later in this talk. Of course, we can't know how accurate that map was because we didn't have any photographs to compare it to. So in the 20th century, photography was applied to astronomy for the first time. And here you can see one of the first astronomical images of Mars. This was taken at the Lowell Observatory in Flagstaff in northern Arizona. It's a place dear to my heart. I lived in Arizona for many years. So Percival Lowell, he used this telescope to observe Mars, and he saw things that he were convinced were canals made by intelligent Martians. And that kind of seems a bit funny now with what we know about Mars, but I think we have to remember it's really hard to be completely objective when you're doing science at a distance like this. And I think even in my field, I look at satellite images of Mars. We have to be really, really careful not to bring our preconceptions with us, because we're looking at this planet from orbit or through a telescope. And there's no field work in most places to confirm what we're seeing. So we have to be careful. So this is a cutting edge astronomical image of Mars. It's the Hubble Space Telescope. You can start to pick out some geology, perhaps. You see some different structures on the surface, different colors. You see perhaps a polar cap up here, maybe some features in the atmosphere. So that's really amazing. But I would still argue that this is mainly astronomy. I think you can only really do geology on Mars by sending a spacecraft there. So this is what happened early on in the 60s. So Mariner 4 sent back the first images of the Martian surface. That was a NASA mission, and it flew by Mars. And here on the left, you can see this image. It's pretty grainy. It's not the greatest quality, but certainly good enough to pick out some structure. So what you can see here are impact craters. So this is where things have smashed into the surface and excavated holes in the ground. And these are well-known features from anyone who's looked at the surface of the moon. So I think if you were seeing these images and this is all you knew about Mars, you might think that Mars was quite like the moon. Now, the second image shows a different thing. So this is from Mariner 9, which orbited Mars, sent back many more images, much better quality. And it saw things like volcanoes, it saw dune fields, and it also saw things that you can see in this image, which were branching valleys. Now, the key thing to see here is these are quite deep, they're quite wide if you look at the scale bar, and smaller valleys feed into larger valleys, which in turn feed into even larger valleys. These are just like river valley systems on Earth, and these essentially created by water that cuts down into the bedrock as it flows downhill. This really opened up a new aspect of Mars study. So that was the 60s and the beginning of the 70s, and since then there have been dozens of missions sent to Mars, orbiters and landers. So this image only shows the ones that are currently active. There are 7 orbiters, I think anyway, I hope I haven't missed one out, and 3 active landing craft. 2 of them are rovers. Here's Curiosity and here's Perseverance. One's just a lander. This is the geophysics lander, sorry, InSight. And there's also, for the first time ever, this little thing down here is a helicopter called Inspiration. So I think what this means is that each of these missions are pretty expensive. There are hundreds of millions or perhaps even a few billions of pounds or dollars or euros to create. So humanity really cares about exploring Mars, else it wouldn't spend its hard-earned cash on it. So if you remember those Mariner images, if you compare them with modern observations of Mars, this is just an example. So here we have a Marsi image. That's of the whole globe of Mars. These can be taken every day to monitor the weather, monitor surface changes or dust in the atmosphere. Really astonishing quality to happen every day. Here on the left, this is my type of image that I use constantly in my research. This is a high-rise image. So this is an orbiting spacecraft with a very powerful camera. It looks down on the surface and it can spot things that are only about 60 centimeters across. The pixel size is 30 centimeters. That's mind-blowing. So here in this image, which is also in color, by the way, I should point out, you can see this lovely fractured bedrock over here, and you can see these wonderful ripples over here. And these would have been caused by blowing winds, moving sand. And then right in the center, what you can actually see here is the Perseverance rover itself. So this camera is so good, it can pick out vehicles, spacecraft on the surface. The little ears either side are actually the blast zones where the rocket motors disturb the surface during landing. And here on the right, this is a very hot off the press image. This is actually taken with the incredible zoom capability of the camera on board Perseverance rover. It's called Mastcam Z, Z for zoom, and it's showing some beautiful geology in the distance. So the quality of data available for Mars now is simply astonishing. So let's talk a bit about Mars. Let's talk about the big picture. So here you can see Mars. Mars is obviously much smaller than the Earth, and that explains why the gravity at the surface is also lower. It's about a third. And it also partly explains why it's got a thinner atmosphere. So Mars's atmosphere is entirely made of carbon dioxide. It's 200 times thinner than Earth's. So at the surface, the pressure is only about 5 millibar, where Earth's is around 1,000. So it has got an atmosphere, but it's a very thin atmosphere. It's quite close to being a vacuum in many ways. It's the fourth planet from the Sun, one out from Earth, and that explains something else. That explains its distance from the Sun means it's very cold. The mean annual temperatures on Mars, -50 to -60 degrees C. So it's pretty chilly. Now we also know that Mars has got lots of big geology. So for example, Olympus Mons is the biggest volcano in the solar system. Valles Marineris is an enormous canyon system, dwarfs the Grand Canyon. And also, as that picture I showed a few slides ago of all the missions, it's the best explored planet after Earth in the solar system. So that last view showed a realistic picture of what Mars's globe looked like. That isn't really how I see Mars. This is how I see Mars. I visualize Mars through its topography. So what you're seeing here is a colorized image that shows the heights of the different regions of Mars. Blue is the deepest bits, and red, brown to white are the highest bits. And this sort of data really help us understand the geography. Let's take a look at some key features. First of all, there are some big holes in the ground. These are impact craters, or when they're really big, we call them impact basins. Again, these are caused by things hitting the Martian surface. These big ones are probably caused by the impact of asteroids or comets, really going at very fast speeds, possibly up to 10 kilometers a second. So that's a big bang. Now we can also see here the Tharsis province and the Elysium province. These are volcanic plateaus, huge amounts of lavas and other volcanic materials piled up on the surface. And each of them are capped by smaller, discrete volcanoes. See those here, here, and here. And this is Olympus Mons, away at the side. You'll see Valles Marineris, the canyon system. And the other thing that I think is most obvious about this is the fact that the north is much lower than the south. The north is also smoother. The south has got sort of a rougher texture. It's got many more of these little impact craters in it. And we call the difference, the boundary between the two, we call that the dichotomy, or sometimes the dichotomy boundary. I think the jury's still out as to why Mars has this difference in its topography. I think a lot of people think it's because huge impacts happened early on in Mars's history into the northern area, and that excavated all that material. Whichever way you look at it, though, the dichotomy is one of the earliest things that happened in Mars's geological history. So I've talked a little bit about time on Mars. And so on Mars, like on Earth, there are geological periods. Now, unlike Earth, the geological periods are defined essentially by how many impact craters you find on a given surface. Impact craters happen all the time. So a surface or a lava flow, for example, that is exposed to the Martian environment for longer will accumulate more impact craters. So the more impact craters something has, the younger it is. Now we call these different ages the Noachian, which is the oldest, Hesperian is in the middle, and then the Amazonian. There's also a pre-Amazonian, but there's basically very few examples of terrains that could be called pre-Noachian. These little yellow things splodged around, these are the products of impact craters, actually. So this sort of hides the true ages of what's underneath. So you can sort of just ignore those in this figure. What I hope you can see, though, is the Southern Highlands is mainly covered in blue, and the Northern Lowlands and some of the volcanic plateaus are mainly covered in green and orange. So the Southern Highlands is really much, much older. So now on to Mars's geological history. So I'm going to talk about everything there was in the whole of Mars's geological history. Well, no, I can't do that in just 45 minutes. There's a huge variety. There's a huge amount of things to talk about. I think I'm going to summarize using this really wonderful figure. And the take-home message really is geological activity on Mars has waned over time. So here we have the Noachian, Hesperian, and Amazonian, the same as what we saw before. And what we can say is that Mars once had a magnetic field, but at some point, probably during the Hesperian, that waned. Most of the really big impacts that created the big basins happened during the Noachian. Volcanism, there was obviously a lot of volcanism to form these big plateaus, and that began in the Noachian and continued through the Hesperian, with a few little bits of volcanism happening later in Mars's history. Now, the surface chemistry is an interesting one. We find minerals on the surface that seem to have been formed by the process of interacting with liquid water. So these could be clays or sulfates, but we only tend to find those in the oldest regions of Mars. When we look at the youngest regions, they have ferric oxides, for example, that are formed in dry conditions. Now, I'm going to talk a little bit about this more, so I won't say too much about that now, other than, on the whole, we feel that Mars was wetter in the past than it is now. Now we know that it's very, very dry, and so during the Noachian and perhaps the Hesperian, there was a lot more water around. Well, why explore Mars? I mean, okay, it's got an interesting geological history, of course, but why have we spent all this money going to look at it? Well, I think a big reason is simply curiosity. The human species loves to explore. I can see we've set some polls up there. That's great. But the other is the question of life. So if we compare Mars's geological timescale with the terrestrial geological timescale on the Earth, there's a very clear difference here. Archean rocks on Earth are actually really rare, but the earliest life happens on Mars, or began to get going, at around 3.5 to 4 billion years, something like that. So we know that rocks of that age are very common on Mars and very rare on Earth. So perhaps if we want to go and look for rocks that might contain evidence of the origin of life, maybe Mars is a better destination. So that could be the case. Should we send humans to Mars? So it looks like 77% of people have said yes. That's interesting. They can certainly do a very good job. I always think that a single Martian geologist, a good Martian geologist on the surface, could do the work that a Martian rover could do in perhaps several months, just in a week. So humans are very adaptable. So I would have said yes as well, I think, provided it was safe. So just to come back to this, I think this question of life, we know Mars was wetter in the past. We know Mars got lots of very ancient terrains, lots of ancient rocks. So exploring for life is one of the main reasons that we're trying to understand the geology of Mars. And in fact, most of the missions sent to Mars go to sort of Noachian regions for that very reason. Okay, so I'm now going to talk a little bit more about what geological evidence we have that can tell us about the Martian environment during the Noachian. Well, the Noachian surfaces, they show a lot of evidence for long-lived liquid water. So a good example of this is something we call valley networks. And valley networks are just what they say they are. They're networks of valleys. So they can be hundreds of meters deep, sometimes kilometers long. They can even be hundreds of kilometers long or more. Sorry, I said kilometers wide, hundreds of kilometers long. Now, they have a distinctive pattern, a branching pattern that you may remember from the Mariner picture. What you can see, especially over here, is where smaller valleys are feeding into larger valleys, feeding into even larger valleys. And they are branching to form these like large main trunks. So again, very similar to what we would see in a river valley system on Earth. Some of them end their lives in impact craters, perhaps to form lakes. Others go all the way to the dichotomy boundary and perhaps spilled out into the northern plains. Others we can't really say anything about because they've been buried or eroded away. Now, they've almost certainly been carved into bedrock, and that's almost certainly by the action of flowing water. Those sort of valley networks have been known about for a long time. They've been recognized in orbital images for decades. In the past 15 years or so, there's been another type of river feature that's been recognized more and more widely. And so there's a great example here on the left. This is a feature called Aram Dorsum. And you can see it has a very river-like branching pattern. This was a region I worked on a lot during ExoMars rover landing site selection. Unfortunately, my site, this one wasn't selected. Came sort of second runner-up or something like that. That's okay, still an interesting place. What you can see is it's a flat-topped ridge. So it's not a valley, it's actually a ridge. And here's a smaller ridge that feeds into it. Now, another important feature of these types of things is that they're often set within smooth material either side. And here on the right, you can see part of the ridge has actually been buried by some of this smooth material. So how can a ridge once have been a river? Well, the answer really lies on Earth. So, and that's the best way to explain these things. So here on Earth is it's an example of a feature that's basically identical. This is in Utah, near a place called Green River. You can see this flat top ridge, like this, a bit of branching as well. And on the right, you can see a little diagram that explains it. So what we have here is a river that was once flowing within sedimentary deposits. It wasn't carving through bedrock. It was depositing and then moving around within fine material that it had brought there itself. So within the actual active channel would have been sands or pebbles. Outside of the active channel would have been finer materials, clays or muds. Now, when the channel became abandoned and was buried by later deposits, those sands would have formed sandstones. And then when that region underwent erosion much later on, the sandstones, which are normally better cemented, are much more erosion resistant than the floodplains. And so they're not eroded as quickly. And though if you have even more erosion, you can find these caps of sandstone sitting on top of mudstones or shales that have been eroded away. And that's exactly what we're seeing on Mars. The important thing is this represents a river that isn't just carving through bedrock, it's depositing sediments around it as it goes. So there's a real diversity of river systems on Mars. I've tried to put them here into context in a sort of a terrestrial, sort of A-level geography, physical geography diagram. And so the valley networks represent the source region and the transition zone, where there's a lot of erosion going on with this water. Then if you come down into the floodplain zone, this is where I think the inverted channels and their associated deposits are found. Now we're finding more and more of these inverted channels, and often we find them in places where we don't find valley networks. So I think that's really, really important. What it really says to me is that if we go looking in Noachian terrains, we're probably going to find far more deposits laid down by rivers than we had previously thought when we were only things we could see with the valley networks. So I talked about rivers, so now I'm going to talk a little about lakes. Now, we refer to these as paleo lakes. That just means a hole in the ground where there was once a lake, basically. There have been several hundred proposed paleo lakes on Mars, and they're mostly in terrains that were Noachian and some of them in the early Hesperian. So these are the really ancient periods on Mars. And the evidence that makes you think it was once a lake is basically because you've got an inlet valley, part of a valley network perhaps, then you've got an outlet valley. And the only real way you get an outlet valley is if the whole crater had filled up with water and overspilled its rim. So another bit of evidence sometimes can be terraces, like you can see here. Sometimes they form at a consistent elevation. So that could represent a consistent standing body of water. And the other thing we often see in these lakes are fan-shaped deposits. So what's happening here is in the inlet valley, the river is carrying sediment, but as it breaks out into this wider space, it can't carry as much sediment, so it deposits it. And that forms a fan, as you can see here. This one almost fills up this entire crater. Now, if that fan is deposited onto sort of dry land, it's what we call an alluvial fan. If it's deposited into a standing body of water, so if the lake was here already, then it forms what's called a delta. Now, lakes are interesting, and in fact, they're so interesting that the most recent Mars rovers have been sent, to ancient craters that were almost certainly lakes. So there's two reasons for this. If you look at these wonderful artist sketches here, you can see there was almost certainly a lot of water around. And this would have been a nice habitat for any ancient life on Mars, because we think that life thrives better and needs water, in fact. But also in the center of a lake, away from any disturbances, any fine-grained material that's carried in could be deposited in nice low energy environments at the bottom of the lake. And that's really good for preserving evidence of past life, if ever it was there. So I'm going to talk a little bit more about Gale Crater, which is where the Curiosity rover has been, I think, for the past 10 years or so. So this is just some examples of some of the data collected by Curiosity. So in those 10 years, Curiosity has traversed about 25 kilometers across the floor of Gale Crater, examining rocks as it goes, and it's found convincing evidence within the rock record that liquid water was present in the ancient past here. So on the left here, you can see these very fine layers. So these are laminations of a mudstone, a very fine-grained rock. These are just the sort of things laid down in deep or quiescent lake environments. So this would be a long way away from where any stream or river meets the lake. Now here in the middle, this is a rock type called a conglomerate. And this was found right at the start of Curiosity's journey. And what it is, it's formed of many small rounded pebbles and coarse sand grains, all stuck together. And these are very similar to the types of rocks you might expect to see in the tops of one of those inverted channels that I spoke about just a few slides ago. These represent the part of the system where water was traveling quite fast, and it's able to move quite large grains. Now, this is a smoking gun for the action of flowing water. It really is. It's incredibly lucky find, I think. And even here, outside of this, you can see pebbles that have been dropped out of this conglomerate. Here on the right is a terrestrial example of a conglomerate, and I think it shows quite nicely how similar the two are. Just a couple more slides from Gale Crater. These are two images showing at the top a view looking down into the south, looking to the south down into the crater. You can see it's a little rock here. And this second image at the bottom, this is a bit further into the crater, and it's more looking to the west And this is actually the same rock. So you can imagine that the rover was positioned around here. Now in this top one, we can see rocks that are fine-grained sandstones, and they've got some larger grains in there as well. So that suggests they were laid down in water, and they're dipping down towards the center of Gale crater. Now these are what's known as cliniforms, and they represent sedimentary beds that have been laid down on slopes, and these are often at the margins of a lake or a sea, anywhere where you have sort of a slightly steeper slope, and they're often formed as part of a delta. Here at the bottom with this sort of edge-on view, you can see some of these in even more detail, see how steep they are. So on the left is a stratigraphic column, and really what that is it's just a diagram that shows all the different rock types and how they fit together one on another in terms of the timing of when they were laid down. Now, these rocks here form part of the Kimberley, and this formation is a formation that describes the edge of a lake, basically. The Murray Formation, that describes some of the mudstones that we saw, and that represents a lake formation. At the time of writing, I think people were unsure as to how the Murray and, well, actually the whole group, the Murray and the Bradbury fitted together, sort of interfingering between the two. It's very hard to work out which was specifically on top of each other. The thing I want to really show here, though, is there's an awful lot of complexity. There are multiple periods brought out in this rock record that suggest the lake advanced and then retreated. So the story we're getting back from Gale crater is much more complicated than simply a transition from an early wet phase on Mars to drier conditions later on. It shows that the environment here was really dynamic and complex and changed over time. And none of that information would have been possible to get unless you looked at the geology of what was going on. I'm going to finish with this one for Gale anyway. It's not all about water. I'm going to show you this slide. Here's a beautiful picture. And what you can see here are a different type of sediments. Again, they're fine-grained sandstones, but these were laid down by winds. This was part of a big dune field. So up here, you can see these rocks, a nice cross-bedded sandstone. They're part of what's called the Stimson Formation. They're sitting on top of this Murray Formation, which was laid down at the bottom of a lake. So what we're seeing here is evidence that at some point in time, this lake had dried up completely at this location, and instead the environment was arid and sand dunes were covering it. Now here in front, there's also some modern sand dunes. These are probably formed in the last hundreds to thousands of years. So they've actually got a ripple-like shape and composed of quite dark sand. I say a couple of things about Perseverance. Well, Perseverance has really only just started exploring. So it's landed somewhere around here. This is the inlet to the Jezero crater. This is the big fan-shaped deposit that many people think is a delta. And on the bottom, you can see this beautiful panorama. This is one of the first really big images taken by the rover. It actually extends a lot further than this, but the center of it is looking this way. And what you can see here is the edge of this fan shape here picked out. And in the very far distance at the back, all the way up here, this is the edge of the crater rim. So a key goal for Perseverance will be to determine if this was a delta or not, and whether this crater actually held a lake, because that's the interpretation made from orbit. So it's only just started exploring, but already the geology is astonishing. So I just want to show this one really, really quickly. So this is a section of that image I previously showed. But Perseverance has many instruments, and this is an instrument called SuperCam, and it's got a thing called the Micro Imager, which is essentially a telescope on top of the rover. And it was able to zoom in here on this thing, and you can see some amazing dipping layers here sandwiched between some horizontal layers. So again, these could be cliniforms. So this could be evidence that this perhaps was a delta. So I'm not going to say much more about that because I think there's many years of exploration still to come before we really tweak the story out of the rocks of Jezero crater. Well, I've talked a bit about deltas. Deltas don't just form within craters. Not all valleys terminate in impact craters either. So there are many fan-like features or things that are probably deltas at the ends of valleys, and they form at the dichotomy boundary. So this little study here, which was about 10 years ago, in the center, you can see a topographic map again. So we're actually now looking down the Mars North Pole. Blue is low, or purple is the very lowest, and red is high. And each of these little triangles represents a delta or fan-like landform that forms at the end of a valley. And when they analyzed this data, they found that many of them actually have the same elevation. And because they're not forming into a crater, they're forming into a giant hole in the ground. And if they're all forming at the same elevation, that suggests that maybe they were all forming into the same body of water. So people have argued a lot over the years about whether Mars ever had an ocean. I think this study is one of those that really provides good evidence that it was a past ocean on Mars, and this would have been during the Noachian. So I'm going to summarize a little bit about the Noachian. There's a lot of geological evidence for the action of water, not just erosion of bedrock, but transport and deposition of sediment. You can see the evidence in the geomorphology, so looking down at the landforms. You can also see it in the rock record, looking at outcrops from the ground. So what this really means is that at some point, the climate must have been able to support long-lived surface flows of water and lakes. So these are the sort of geological reasonings that people have made over the years to come to the conclusion that Mars during the Noachian was warmer and wetter than what we see now. That's also explains why so many missions are targeted at Noachian terrains. I'm just going to quickly come into the Hesperian now. So the Hesperian was I think it's fair to call it a transitional period. I think a lot of the same things that were happening in the late Noachian continue to happen into the Hesperian, and also lots of things that we see in the Amazonian probably got started during the Hesperian. One thing that is clear that happens, I think, during the Hesperian is that Mars's climate changed dramatically, and we think this is linked to the loss of its magnetic field. So what we can see in this nice little diagram is an illustration of solar wind particles hitting the atmosphere of Mars, and then the green and red ones are then being stripped away. Now, charged particles from the sun, if Mars had a magnetic field, these would have been deflected, like a deflector sort of ray, moving them away. So because Mars lost so much of its atmosphere during the Hesperian, it became colder, had a lower surface pressure. Water wasn't able to be stable as a liquid at the surface, and it migrated underground, perhaps as a liquid forming aquifers, or maybe as ice. So I'm going to show you one more thing about Hesperian, and that's even though we think of it as not having had an awful lot of activity in the same way as the Noachian, there were still some really enormous geological features being formed, and also to do with liquid water. So here on the left is a picture of what we call an outflow channel. It's called Kasai Vallis. And on the right, you can see the topography data that goes with it. Here, blue is low again, and then the top most bits are yellow. Now, it's a really big feature, 1,800 kilometers long. It's about 2 kilometers deep in the deepest places and hundreds of kilometers wide. This little red bar here shows a cross section. So that's what you can see here. So this individual part of it was 40 kilometers wide, 2.5 kilometers deep. That's an enormous, enormous canyon. Now, they're very different to the valley networks. They don't have this contributory branching shape. They often start from a single point rather than a distributed source of smaller valleys. And many seem to actually come from underground. So they start at chasms or rifts or collapse regions. So what we think has happened here is huge quantities of water, what we would call a mega flood, has erupted onto the surface somehow. And it has essentially torn through the bedrock of this area, removing everything. I mean, I find it incredible to imagine anything that can dig a hole 2.5 kilometers deep and 40 kilometers wide, and then continue to do it downstream. That's a huge amount of energy. Now, we've had mega floods on Earth. So the biggest mega floods on Earth, some examples of those are from the North American Missoula floods that happened about 12 to 14,000 years ago. In Washington state, you can see the evidence of these, similar but smaller landscapes. And they were thought to form from flows up to about 10 kilometer cubed an hour. That's still an amazing amount of water. Can you imagine a kilometer cubed of water? However, the Kasai floods, when people have analyzed the landscape, they were 100 kilometers cubed an hour. I just think that's mind-blowing. A huge amount of material, almost too much to believe, really. So I'm now going to just quickly skip into the Amazonian. It's the longest period. 3 billion years is a very long time to have as a single period. And I think most people feel that the Amazonian is a bit boring. It was cold, dry, and geologically inactive. But I don't think that's true, actually. I think lots of things have happened in the Amazon. So here on the left is the results of a study to see when the various different Martian volcanoes had their last gasp of activity. It was dating the last lava flows on the surface. So down this side, you can see age in billion years. So Noachian's down here, Hesperian, then Amazonian. These are all the different volcanoes. And each data point represents a measurement made by basically counting the number of impact craters on top of that lava flow. What you can see is there's actually quite a few lava flows that appear to have happened during the Amazonian. So it wasn't all dead and boring. Also, another thing that I spent some time studying is a small mega flood channel. Well, it's hard to say a mega flood channel can be small, but Athabasca is one of the smaller ones. It's created these lovely streamlined islands as the water has rushed through there. But this is only perhaps tens of millions of years old. So that's yesterday, a blink of the eye in Martian history. So things are still happening in the Amazonian. Now, one thing that is certainly true about the Amazonian is it's been cold. And so because it's so cold, any water ice or water vapor in the atmosphere will condense onto the surface into pore spaces in the regolith. Now, regolith is just what we call planetary soil. Okay, so if you say regolith, just think of it as soil. So if you imagine that you have ice trapped in the regolith and perhaps some more sand or dust is blown over on top of that, that ice can get stuck in the regolith for a very long time. And over hundreds of millions of years, that has happened, and it's created lots of ice in the Martian regolith. And we know that because we can dig into the surface and reveal the ice. So here on the left, this is a natural digger, a new impact crater. So it has struck the surface. It's only a small impact, and it's dug up some white stuff. Now, if that white stuff was a white rock or white colored debris, a few months later, that would still be there. But here we see that it's disappeared. So that suggests that it was ice that was dug up and it's sublimated in the thin Martian atmosphere. It's disappeared. Now, also we had confirmation of this. The Phoenix lander landed in the very high north region of Mars. And it had a little digger attached to it, and it dug these trenches, and it found white deposits at the bottom of these trenches. And these little insets show that some of these white deposits disappeared in only a couple of days. So really, it found ice, and quite large amounts of ice actually, in the regolith, and only a few centimeters below the surface. And I think that was really good because that agreed with the model predictions the team had made before they even landed. So that was a nice story. Going to a bigger scale now, when you get large amounts of ice accumulating on the surface, often mixed in with dust or debris, it can flow very slowly due to gravity, and it can form the same sort of things that we see on Earth as glaciers. So here's a beautiful example. Here, a couple of kilometers across, maybe 10 kilometers long, you can see how it's flowed down through this breach in these mountains and has sort of splurged out onto the plain underneath. That's a technical term, splurged out. If climate changes, these degrade, some of the ice within is lost, and a debris cover forms on top. Where you have different topography, you can get even more crazy shapes. So this one has formed in a crater, and because it's coming down from all sides, it's formed this amazing concentric crater fill. It's worth pointing out that most of these glaciers are thought to have formed without any melt at their bottoms. On Earth, lots of glaciers have lubricated bottoms, and that enables them to slide much quicker. So they move orders of magnitude faster than these Martian glaciers would have done. Most of these are Amazonian, quite late Amazonian, in fact, perhaps tens or even hundreds of millions of years old. But we do see glacier-like things that date as far back as the Hesperian on Mars. So there's a long history of ice moving around and flowing on the surface on Mars. Now, I did say most of them were dry. Well, in the last 5 years, there's been a few studies that have come up with hints that this isn't always the case. This is actually a study that I was involved with my colleague Coleman Gallagher in Ireland. And what we see here is a remnant glacier in a sort of a valley between some uplands area. And then in front of it are some strange surface shapes. So here are sort of branching river-like features. Here are sort of strange hummocky materials, and down here are intertwined ridges. Now, we think these are eskers, and eskers are deposits of sediment that have filled a tunnel that was once underneath a glacier, and water flowed through it. And in fact, what we're seeing here are streams caused by melting of ice when the glacier had retreated further. So these are very rare to find any Amazonian glaciers with evidence for melting. Another half dozen at the most have been identified throughout Mars. So this is definitely a new thing to look out for. And again, a little hints that a little more was going on in the Amazonian than often we think. Right, well, I'm going to finish by talking about present day Mars. What's going on now? Well, here you can see a beautiful animation of Mars. This was taken by the Marcy camera that I mentioned before. You see, a few days later, we can't even see the surface, apart from perhaps there's some volcanoes sticking up. So dust has gone into the atmosphere. So this is a planet encircling dust storm that's kicked off in only a few days. Now, you get these every 2 or 3 years on Mars, and it demonstrates that the winds at the surface are strong enough to pick up dust. There's an active sediment cycle going on. Looking at a totally different scale, this was taken by Curiosity, and I think this is one of my favorite images I've ever seen on Mars. What it shows is, over one day, a set of dark sand with ripples in. The wind is blowing them, so those ripples are migrating ever such a small amount, but only in one day. Sand transport is happening on Mars right now. You can even see the tracks left by the rover blurring away. Now you can imagine that, and then over several billion years, or several 100 million years, you really can see how these big dunes that you see all over Mars form. So you see the ripples on the backs of them, the steep slip faces at the front of them, and they're traveling across this white fractured bedrock. Some of these are hundreds of meters high. They can be kilometers in size. They can be really enormous. Got a little animation here. So this is a before and after image of a linear dune, and it's extending. So 2008 was the first, 2016 was the second image. So it's moved 20 or 30 meters in 8 years. So not as quick as terrestrial dunes migrate, but still pretty good, several meters per year. Another thing that we see is the action of dust devils. So this was taken from a hill by the Spirit rover, which was in Gusev crater, and it made these amazing time-lapse videos, essentially, of dust devils. Dust devils are dusty whirlwinds. They suck up dust and train dust from the surface into the atmosphere. And these are, beautiful examples. They're probably a few meters to a few tens of meters across, these ones. You can see that the ambient winds are blowing them together all in one direction. Now, I know about dust devils because I've used to study dust devils on Mars. I hope my video is going to work. Oh, I don't think it is. Oh, I failed right at the end. I thought I was going to show a video of a dust devil on Earth. I'm sorry, I can't do that. Maybe we'll see if we can get it posted at the end for the recording. I was just going to show you a video of dust devils on Earth. So other things that are happening on Mars today, the one on the left needs a little explanation. So what we're seeing here is a steep slope going from left, that's the top, down to the bottom at the right. It's a layered slope, and at the top is ice, probably carbon dioxide ice, because this is in the far north. What has happened here is some of this slope has collapsed and it's created an avalanche, and the high-rise camera, this amazing camera that has just snapped a picture just at the right time to capture this avalanche in action, which I think is really amazing. On the right, this is a totally different time scale, but it also shows things moving down slope. Here, the slope, the top of the slope is up here at the right, and the bottom of the slope is down here at the left. And over several months, you can see these little tongues getting bigger and bigger and fading away. So these are going slowly because we can see them across several images taken months apart. And no one really knows what they are, but they happen in the warmest parts of the planet with the steepest slopes, and they seem to recur every year or every Martian year. So they're called recurring slope linii. Some people think they might be to do with liquid water, perhaps, flowing just below the surface of these dusty deposits. Now, the final thing about present-day Mars, I've mentioned impact craters, and impact craters are always happening everywhere you go. So this is a new 15-meter diameter crater. These images were taken about 2 years apart. The one without the big splurge is the before, and then the big splurge image, that's after. And even though the crater itself is only 15 meters across, that's about the size of my red spot, you see how it's thrown out all this debris, 500 meters away. And so this is a tiny crater. You imagine the mess a much larger impactor would cause. So I'm going to summarize what I hope I've told you. I see we've got another question in progress whilst I'm doing that. I think impact craters, volcanic processes have shaped the Martian surface throughout its entire history. The oldest terrains host extensive deposits of sediments, and more than we ever thought before, I think. We've seen that they're laid down in water, in lakes, in river floodplains, and perhaps even in oceans or seas. Now, we saw that the Hesperian period was a transitional period. Mars climate changed a lot during this period, but a lot of Noachian processes continued through into the Hesperian. Lots of people like to say that the Amazonian was cold and dry and boring. Certainly it was dominated by ice and winds, but I think volcanism and liquid water also played a role. And so Mars is still active today. Winds, impact cratering are the most obvious process, but I wouldn't be surprised to see a report in the next few years of active volcanism, a new volcanic lava flow or a new explosion of an explosive volcano on the surface. When do you think the first humans will land on Mars? Well, most people are not as optimistic as, I don't know, perhaps SpaceX are. So the majority thinks 2040. Oh, well, I'll be in my 60s by now. By that time, so that'll be a shame. I was hoping to get a ticket myself. So, all right. Well, what's next? I have one more slide, really. And that's really just to say that the search for life on Mars, which I think is really helped by a good understanding of the geology, is focusing on Noachian terrains that have evidence for water. So the mission I'm involved with, I have to click off the poll, is the ExoMars rover, the Rosalind Franklin rover. So this is a European Space Agency mission, and it has one goal really, is to search for evidence of ancient life on Mars. So it's an amazing piece of kit. It's got a hugely capable onboard laboratory, and it's got a deep drill sampler that can drill 2 meters below the surface, extract samples, and then it can actually deliver them into this little hole here that brings them inside the rover for the laboratory analysis. Now it's landing in a place called Oxyoplanum. It's a Noachian site. It's got hydrated minerals thought to form with the action of liquid water involved. And actually in one part of the site is the termination of a big ancient river network, so a valley network, and it's got a great big fan at the edge as well, which may be a delta. So it's a really great place that brings lots of different bits of evidence together. So we'll be landing in 2023, and I hope, fingers crossed, it'll all be safe, and I'll be coming back maybe in 2024 to give another talk about what ExoMars rover has found. I see from the poll that not many of you would want to live on Mars. I think I'd probably agree, though I think when I was 20, I probably would have said yes. So, all right. Thank you very much. If there's any questions, I'll try my best to answer them now.
Thanks so much, Matt. That's absolutely fascinating talk. And I really had no idea there were so many rocks and landscapes on Mars that's so similar to Earth. And those images of the dunes are just beautiful. We've got a lot of questions, so don't worry about that. So let's start with some ones that we had from Zoom as we went through. How can you tell from the images that you were showing the difference between an impact crater and a volcano?
Well, it can be very difficult, especially if they've been heavily eroded away. So ancient ones, they, in some ways, they both look like holes in the ground. But often volcanoes will have lava flows coming out of them. They might be arranged in lines showing that, whereas they're formed on top of an underground fracture or something like this. Whereas impact craters have a very definite rim morphology, a bowl shape, and they have an ejector blanket, a debris blanket around them, like a little collar. So sometimes it can be very hard to tell the difference. 99% of the time, we can normally do it based on our knowledge from Earth and other planets like the Moon.
Yeah, Earth is quite handy for understanding Mars.
Oh, we could do a whole talk on Mars Earth analogues at some point.
Lots of people asking, why is there no water on Mars now?
Well, there is a lot of water on Mars. I think it's just trapped deep underground. So, when the surface becomes so cold, it's hard for it to be mobilized, and it's sucked out of the atmosphere and freezes onto the ground where it gets buried. Now, some people think that if you went really deep underground on Mars, same as on Earth, it's warmer at the center of the planet. You would meet a depth where the heat coming up would match the cold coming down, and perhaps you could have a beautiful underground liquid water aquifer, which in fact is a really good alternative environment for habitability. So, I think not many people think there's life on Mars at the surface now, but maybe there is life on Mars underground in one of these, I don't know how you call it. It's like a spa hotel underground for Martian.
A Martian spa hotel. That sounds fantastic.
Yeah. Well, it does sound good.
It does. So some more people asking, what's the current theory on the origin of water on Mars? Where did it come from?
It's the same as most planets, which it was either there when the planet accreted out of the nebula from which the whole of the solar system formed in certain amounts, or it was brought in by comets and asteroids that came in from other parts of the solar system. Okay. So, a big comet has a lot of water.
So it's either there at formation or it arrived on a comet or an asteroid. Okay. How did Mars lose its magnetic field? A lot of people are asking.
Well, I think that's a question for a geophysicist, really. The normal explanation is Mars was a smaller planet, so it lost heat more quickly, so it stopped having a nice liquid core. It's made of metal, and so if that isn't there spinning around, then you don't generate the magnetic field. So basically, it's another sad part of being too small, really. So it just wasn't able to maintain the dynamo at the center of the planet to keep the magnetic field going.
So we see lots of volcanoes on Mars, but is there any evidence of plate tectonics like we see on Earth?
Well, when I practiced this talk, I realized it was going to be 2 hours long or something ridiculous. I had to take my slide about plate tectonics out. So no, there's no plate tectonics, and at least we don't think so. There's a couple of places that look like it might have just got going, but there's no consistent pattern where you have continents which are quite old and ocean basins that are quite young, and there's certainly no spreading ridges where the age of the deposits radiate out from those spreading ridges. Okay. So it's essentially a one shell planet, really.
We have a couple of questions about the missions and rovers that have been to Mars. Someone asks, will the ExoMars drill be an improvement on the InSight drill, which had some issues?
Well, they're very different things. So the InSight drill is a mole. So essentially it's a thing on a tail, and it bangs itself into the ground. Whereas the ExoMars drill is actually a big drill, an auger, and inside it's got 3 separate rods. When it gets to the end of one rod, another one slots in on top, and then the final one slots in. So not only does it actually drill as, rather than just sort of bumping its way through, it can have the whole of the weight of the rover behind, essentially pushing it down. A bit like me with the the power drill trying to get through the walls. Okay. To hang a picture.
And somebody else asks, how is it that Perseverance is able to take all these images? How is it doing that?
Well,
and curiosity for that matter.
Amazing engineering, amazing instruments, scientists who are well trained and know how best to target the instruments, and good communication systems. So, you can build a camera. In fact, your phones, everyone who's got a phone has probably got a phone that's got a bigger number of megapixels than most of the cameras on Mars. But of course, sending that large amount of data back to Earth, that's the challenge. There's only a certain amount of bandwidth, your pipe for data can only be so wide when you're going all the way back from Mars. So often that's the challenge. But Perseverance was spectacular. It had more cameras than any other mission, and the cameras are better and they do more things. Some of the cameras do several things, so they can look at images and spectra all at the same time. I mean, Perseverance is an absolute, it's engineering.
Yeah, it's an amazing bit of kit, isn't it? Incredible.
Really I mean, ExoMars will be too as well. I mean, ExoMars will be groundbreaking in many ways. This drill, no one has ever drilled to 2 meters depth before, and it's got really cool flexible wheels, so it doesn't get bogged down in sandy material.
And when is ExoMars launching? When's the planned launch date?
2022. So towards the end of the year, late autumn, I believe, and it lands in. I should know this. June, I think, or is it May 2023? So
so we'll have lots more.
Busy there.
Lots more Mars news stories on our coming up for us in the next couple of years. Somebody asks, how do we name the geological ages on Mars that you've run through in the lecture?
Well, that's an interesting one. It's a little bit tricky to get across. So Schiaparelli's map showed these different areas, and more modern Mars scientists have kept those names. And essentially what they've done is they've used sort of type locations, specific locations that with their geologic skills, they think all formed at the same time. And they've said, we're going to measure the age of these using impact craters. And that's going to be the base for what we're going to call the Noachian or the Hesperian. So Hesperia planum, Noachis, Amazonia planitia. These are parts of Mars, and so those are the type examples that have the ages that tell you about the.
And they're all Latin terms, is that right?
Oh, yeah,
Greek.
I think so. Greek. So, yeah, I'm not a classics man myself.
No, really.
My colleagues are probably turning in their graves thinking of this.
Okay, we've got lots more questions coming in, but I'm going to have to do the last 2 or 3 because we're using up Matt's evening quick and fast.
I don't mind. I'm happy to go on a few more minutes if you want to.
Okay. Do pan-Mars dust storms obliterate or cover surface features? And if so, does that make your work more difficult?
Well, no, they don't, because although it's a yes and no question, they do cover surface features, but it's only a tiny, tiny thickness. So it might be a few microns, maybe 5 or 10 microns. So it doesn't actually affect the shape of what we do, because if you're looking at things in 6 meters per pixel images, or even 30 centimeters per pixel images, having a 2 micron layer on top of things doesn't cause a lot of problems.
Doesn't obscure your view too much.
No. However, what it does do is it obscures the view of spectrometers that might want to look at the minerals. So even a small layer can change the color, and essentially that's what the spectrometers are looking at. That's a big problem. And in other areas of Mars, where it's particularly quiescent, maybe there are no dust devils, maybe the winds are low, the dust does accumulate. And so you can get areas of Mars that are very thickly blanketed with dust. But people don't tend to take pictures of them for geology because they're quite boring, and nobody's going to land in them because they would be a death trap. So they're not very well advertised to the general public, I would think. So it's a sort of image that if I see one, I just skip over to the next one.
Yeah, not interesting. Okay, something on megafloods. Interested in Matt's thoughts on the possible cause of megafloods.
Well, again, the jury is out. It could be that a combination of volcanic activity, so magma moving underground, magma ascending, interacting with an ice table underground, could build a huge underground reservoir of water. That's one mechanism. Could then spurt up like a geyser, crash onto the ground. Another is that if you had something like this happening but more gently, around the margins would be ice. On the top would probably be ice because the atmosphere is quite cold. But imagine there's water bubbling up underneath, and then perhaps that carapace fractures, and then it all comes streaming out. So that would be similar to the Missoula Lake, the terrestrial example that I mentioned. So no one really knows, but it's almost certainly to do with a combination of ice and some form of heating, probably from local volcanism.
Thank you. So there's a couple of really interesting ones here. So somebody asks, with hindsight, looking back at the earlier images of Mars, do we think it was possible that the erosional features on modern images associated with water could have been spotted in the 1960s data?
Well, I haven't been through them for a long time. I did look at a lot of them during my undergraduate, actually, but I don't think so. I think there was only a limited area taken by Mariner 4, only a small number of images. I think by the time we got to Mariner 9, there was a phrase, new Mars. So even in the 70s, I think they had recognized that things weren't as simple as they seemed, and that for a long time there was arguments about whether these were flows of water that were caused by rain, for example, or whether it was all coming from underground aquifers, and those valleys actually were eroding by collapse at the head of a river coming from a spring. So progressive erosion rather than carving from the top down. So, but I think scientists do the best they can with the data they have, and obviously people are wrong. And when better data come along, you're foolish to try to stick to your guns and say, no, I was right all along. What you need to do is just say, oh yes, the new data show I was wrong, and crack on with helping the new interpretation.
Much better data now. Okay, I'm just going to do the last couple. So how many volcanoes are there currently on Mars? How many are identified? or a scale as tens, hundreds, thousands?
I mean, there are tens of big, chunky volcanoes, but there are many, many more, thousands of smaller edifices that are, that could be volcanoes.
Okay.
As I mentioned right at the early part of my talk, it's hard to not to bring your preconceptions with you. There are many things that look like small volcanoes on Mars. There was a paper recently of saying that some of the lava flows might actually be mud flows. So mud under the Martian atmosphere, very runny mud, it boils away and it forms a crust on the outside of it, similar to lava flows. And then if that crust fractures, a bit of mud spurts out and creates another little flow. And that's just what we see in Pahoehoe lava flows. So you can get this idea where multiple different processes could cause similar looking things. In fact, it's got a name. It's called convergence of form. And so we have to be incredibly careful about that when we do studies like this, because until we get down on the surface and hit it with a hammer, we can't ever be sure. Or
we're just
hit
hypothesizing.
Hit it with a laser. So from a rover.
Hit it with a very expensive ExoMars drill.
Yep, exactly.
And then last but not least, I think this is a great question. Where could we go on Earth that looks most like Mars?
Well, I've been to several places. So Chile is good, the Atacama Desert. It's part of the Atacama Desert. It looks very much like Mars. I wouldn't say that the geology is very much like Mars, though. Obviously, Antarctica, bits of Antarctica that aren't covered in ice have debris-covered ice sheets, and they're often used as analogues for Mars. They do look very Mars-like, and they have a similar Mars-like feel to them. And I've also spent time in Svalbard, or Spitsbergen, as it's sometimes known, which it's got a few more bushes and trees. Well, no, not really trees, bushes and leaves, really. But again, that also looks very much like Mars. I think the place I've been to that really, to me, really most looks like Mars is Morocco, out in the deserts of Morocco. But of course, it's a very different climate. So
okay,
if you're asking for an analog, you have to be very clear what sort of analog you want: visual, climate, or geological. So
it's a good scientist answer.
Yeah.
For those people who answered that they did want to go to Mars but are going to have to wait, if you can make a trip to Chile, Antarctica, Morocco, and Svalbard, then that should give you the start of an idea. Okay, thanks so much, Matt. It was just absolutely fascinating, and Mars is worthy of much of its attention. It's such an interesting planet. For anyone that missed any part of this lecture, it's going to be available on the GeolSocs YouTube channel indefinitely for free. So you can go back and watch the beginning if you missed any of that. And the next lecture in our Year of Space public lecture series is with Professor Alan Fitzsimmons, who's going to be talking about the geology of asteroids and comets, which Matt mentioned earlier, may have brought water to Mars. And thank you very much, everybody, for coming. Have a fantastic evening, and hopefully we'll see you next time. Thanks very much, Matt.